The implementation of the variable angle prism is shown in the next diagram. It looks very simple. It is two circular glass plates, very precise optical surfaces. They are bound together by a bellows that wraps around them. That allows those two glass plates to move relative to each other. But inside, there is a special, very high refractive index liquid that is hermetically sealed inside that enclosure. And then finally, as you can see in the diagram, around the rims of both those glass surfaces is a rigid metal frame that holds it together, but is also the interface to the controlling system that I would describe. So, the name of the game is to sense that jolt to the lens as quickly as possible, then feed that to a microcomputer, which makes some calculations, and that in turn will exercise a controlling actuator that's gripping this prism and squeeze it appropriately, either horizontally or vertically, or both, depending on the nature of that deflection. The variable angle prism itself, I described simplistically its structure, but the science behind it involves a methodology of getting that liquid into the prism and then hermetically sealing it. So that seal will last for the lifetime of that lens, a decade or more. Also, that liquid must maintain its optical characteristics over a very wide temperature range that we specify from minus 27 degrees Fahrenheit to plus 176 degrees Fahrenheit. The bellows that implements that flexibility in the prism is a multi-layer plastic. Very special developments took place there because that must retain its pliability over the tens of millions of cycles anticipated in the normal life of a lens. I talked about the electromechanical system that does the actual gripping and moving of that prism. The technology there is the voice coil motor. That's a technology that's developed by many, many companies, including our own. And it's a technology that has become very refined over the years. It's basically the technology that we have in our loudspeakers to move a cone in a loudspeaker. It involves a coil carrying a current, lying inside an enclosure that has a strong fixed magnetic field. If you change the amplitude of the current, you will move the coil. It's called the Lorentz force, the interaction of the current-carrying coil and the magnetic field. If you change the direction of the current, you change the direction of the coil. So it's a coil that's moving. And that is connected to an armature, a non-magnetic armature, that then is gripping the prism. So the beauty of this is it is extremely high force when engaged, when that current is engaged and altered. High force, high speed, no hysteresis. That's important if you want to move that, follow vibrations and move that prism in different directions rapidly. And of course, no overshoot and no backlash. It's the perfect coupler, electromechanical coupler.